All right, there we go. All right, so first off, today's quiz day. So please fill this out before midnight tonight. I will give you guys 10 minutes to do it in class. Yes. The very first one that you'll notice is there's another survey. This is the end of class survey from Meta, my employer. This is the only thing I actually care about. So the Blackboard survey you guys should fill out as well. But if you can fill this one out, that would be great. Any of these answer choices give you points. So it is not associated with your grade. I'm just reminding you to fill it out. Yeah, David? What's the percentage you have on the class? Oh, on the class one, I think you guys are like 10-ish% right now. But it takes an hour?
It does like me, I'm slow.
Oh.
If you want to be like quick, you can do it in 30 seconds.
All right, so here is what we are doing. So the Blackboard survey, I think we agreed on greater than 80% completion from the class. Everybody gets 1% bonus on their final grade, okay? Separately, greater than 90% on this survey, which I know for a fact takes less than 5 minutes, okay? Because I know what the survey asks. If the whole class gets greater than 90%, everybody also gets a 1% bonus. So that's up to 2% points for your final grade. That's a lot, I hope. Anyway, for context, last time for the midterm survey, we were at 83% for the Meta one. So if you filled it out last time and you fill it out again, you still need to convince somebody that didn't fill it out to fill it out. Like just a few people. Actually, just like 2 or 3 people. So, yeah. And again, the reason I can't give you credit for just you filling it out is because I can't know that you filled it out. Okay, just let's make sure I make that clear. Whether you fill out the surveys or not, I cannot know, so that it cannot influence your grade, okay, individually. So I'll give you guys another 2 minutes to hopefully finish filling out this first survey, and then we can start going through the quiz together. Yeah. And then any of these choices will give you credit. So. And if you're having trouble getting to the quiz, if you can get to the course website, this quiz 12, should take you to the link. If you have the slides open, the link is also on the first page. So we've got 26 people in class, no, 29 people in class today. So if everybody fills it out, we're almost at 50%. That includes the folks on Zoom. How do I get more of you to start coming? It's like, January, we had a lot of people here. And it's like, pizza. Okay.
You could also just start like entrance grades.
I don't like threatening people. I'll try pizza.
I think I said that my friend
freshman year, and they ended up getting a massive slap on their hand because they like changed their syllabus and started requiring like attendance because like it's not allowed.
Oh, it's not allowed to change your syllabus. Yeah.
No, we ended up getting curved for their attendance grades. No, one of the professors did the virtual work, and he continued to do it fine until there were 3 people sitting in his room, but 20 people said they were present, so we took a paper that day. Oh,
I think attendance is important. I appreciate all of you coming. I really value it. I enjoy it when you guys are here. It makes it a lot more fun for me. But you guys are adults. You got your own stuff to do. So, if you can't make it, I assume you are making a good decision for yourself that is more optimal than coming to class. But yeah, all right. So let's follow the rest of the quiz. Some of you probably already, I don't know if you finished filling out the meta survey. You can come back to it. If you all submit it, that would be great. Yeah, that's my main feedback, and that is also the main feedback to Facebook in terms of like, what should they do next semester, or if we're going to expand, etc. So just fill it out. Please provide feedback. Question number 2, what is the runtime of the greedy algorithm for activity selection? Assume the input is given in an arbitrary order. Yeah, back there. O of n log n. Yes, that is correct. Why is that the runtime? So the activity, yeah. Yeah. Yeah, you have to sort. So again, so a couple of things you probably need to remember. The activity selection problem is the one where I give you a list of activities with start and ending times. And your goal is to do as many of them as possible that do not overlap, because you can't do multiple activities. The algorithm for that is to sort them by the ending time and then greedily do the activity that ends first, and then do the next activity that does not conflict that ends first. Okay, so with that activity selection problem, which of the following intervals is guaranteed to be part of some optimal solution? It has to do with like why we end up sorting by the ending times. But yeah. Interval with the smallest start time. Can you explain your reasoning?
Any other activities that you
So if you were right about all your statements, your logic is solid. So that's good. We actually sort by the ending times in the algorithm. If you sort by the starting times, it does not work. Yeah. So we talked about this as well. So there are cases where you have a very short activity, and there may be 2 longer activities that overlap with that one. So you don't want to take the shortest one, because then you can only do that one activity. Right? So the shortest activity will not be in the optimal solution. Well, there's only one choice left. But can somebody maybe explain to me why the last choice works? So for this one, shortest interval, you can have this example where you have 2 activities and then you have a shorter one here that overlaps with both. So the optimal solution is to do, activity 1 and 3. Obviously, that solution does not have the shortest interval. So that's not the right answer. Interval with the smallest start time. What that is saying is, basically what this is saying is like, for every problem, I can pick the activity that starts first as the one I'm going to do. But here's a counterexample. You have activity 1, and then you have activity 2 and activity 3. So the optimal solution is to do these 2. But if you pick this one, then you rule out doing those 2. So it's not optimal. However, it is true that the interval with the largest start time will always be in an optimal solution. Can anybody see why? There is always an optimal solution that has that interval in it. Yeah. Smaller finish times. Yeah, so one way to think about it is, so let's consider, so let's say this is our optimal. So let's say we have some optimal solution, right? So these might not be all the activities, but this is our optimal one, which is going to be 1, 2, and 3. Okay. There's a couple of options. Either this interval, this one, number 3, is the one with the largest start time, in which case it's already part of our optimal solution, so it is in our optimal solution. Or there is some other interval here that has a larger start time, right? However, this is also an optimal solution, because I can, instead of taking this activity, I can do this one instead. And because this one starts after the other activity I took, it does not cross out anything that I had taken before. So I can still take all of the activities I took before. And because this one was the last one, it does not cross out anything. You know, it could end here, it could end here, it could end here. It does not cross out anything after. So I can always swap these two solutions. And this new solution is still optimal because it still does 3 activities. Is that, yeah, for folks on Zoom, it's kind of sucks because you guys can't see the whiteboard, but I'll try to point the camera that way. So it turns out that the interval with the largest start time is always in some optimal solution, because you can always create an optimal solution that has it. Okay. Folks are a little confused, maybe, or kind of no. A little bit, kind of, so some people it makes sense, some people not. Okay, this is really important because this is why the algorithm works. This is why we sort by ending time, and we pick the algorithm that ends first. Okay. But yeah, we'll write up some solutions. I'll have Chi write up solutions for the quizzes, so maybe she can also explain it. All right, let's jump to MSTs. So the minimum edge coming out of a vertex is always part of some MST or is not necessarily part of an MST. So if I look at some vertex A, and it's going to have some edges coming out of it, there is going to be some edge coming out that is the smallest, right? What this is saying is that edge always in a minimal spanning tree? I see some people nodding their head yes. Some people.
May not always be, depending on the algorithm that you use. I think Russell's algorithm usually always takes it takes the smallest time. So it could, but at the same time, using that smallest edge could basically rule out the making of this. Like you could not have the minimum.
You're overthinking it.
Have like a larger spanning tree than the minimum. Just because that one vertex, let's say, has a weight of 1. Let's say you use that, but to finish making your minimum spanning tree, you end up having like a total weight of like 30. Yeah. And you could have not taken that edge, and you could have had a minimum, then you could have had a minimum weight of like 20. So it could, but at the same time, it could mess you up if you take it.
I value your, yeah, no, it's a good attempt, but it is always part of a minimal spanning tree. It might not be part of the minimal spanning tree you construct with your algorithm, but it will always belong to a minimal spanning tree. So why is this true? Somebody want to?
Like just the connection of 2 nodes, and that's considered true.
Right. Sort of, but the reason this is true is because you can always consider the cut that cuts this vertex off from the rest of the graph. Okay, as we talked about in our algorithms, for this cut, there is going to be a lightest edge, which is going to be the minimum one. It is always safe to take that edge as part of your MST. So it might not be in the minimal spanning tree your algorithm constructs, but it will always be part of some minimal spanning tree. Okay, so the answer to this one is yes. What about an edge on the shortest path between two vertices? Yeah.
I'm just going to again rephrase this question. Not necessarily, and my reasoning. Very wonky.
Yeah.
Based on what we just said, you have that like some MSU passing, and you're like listening. The idea that taking the shortest path is not always.
Sort of, yeah. So I would say, I think your reasoning is right. I don't know if I fully understood it, but yes, the answer is not necessarily. One way to think about it is that the shortest path has nothing to do with whether you are in an MST or not. We never talked about shortest path in terms of finding the minimal spanning tree. Another way to think about it is you guys should be able to come up with a counterexample where there is an edge on a shortest path that is not part of a minimal spanning tree. You can probably use like 3 nodes at minimum, and you should be able to come up with, I think maybe you need 4, but there are examples where there is a shortest path between a certain set of nodes that is not, none of the edges are part of an MST. Last one, smallest edge crossing a cut. Yeah. Yes, almost by definition. The way we construct our MSTs is anytime you have a cut of 2 vertices, the separation of your graph, the cheapest edge across that cut is safe. It will be in some MST. Okay, that's why our algorithms work, because they essentially pick the edges that are the cheapest one across the cut. Okay. All right, so next one. So assume we run Prim's algorithm starting at vertex A. In order of being added, what are the weights of the edges that Prim finds? Jonathan?
Starting A, you're going to go A to B 4,
okay.
And then you're going to take 1, 2, 3.
Any disagreements with that? Isaiah? Any disagreements with the order in which the nodes were taken using Prim's algorithm starting at node A? So he said, we start at A, we first take the edge with weight 4 to connect to B. Why is that, Isaiah? Yes, because we are considering this cut, right? And the smallest edge across that cut is 4. So we take 4. Now we are considering A and B as their partition. Now we're considering this cut. And the smallest edge across that cut is 1. So we take 1, which connects C. Now we are considering this cut because we have A, B, C in our tree. The smallest edge is 2, so we take 2. Then we consider this cut. The smallest edge out of 5, 3, and 6 is 3, so we take 3. Then we consider this cut, and the smallest edge there is either 8 or 6, so it's 6. We take 6. Once we've taken 6, the whole graph is, we have reached all of our nodes, so we are done. So that is correct. It is this one. Serena, you want to run Kruskal's algorithm for me and tell me the order?
So we start with the smallest edge weight. We start off with 1. That is one cycle. I'm taking 2 and 3. And you can't take 5 without a cycle. So then you will take 6.
Cool. Any disagreements? You guys comfortable running this algorithm on arbitrary graphs? Great. Expect a question on your final about that. Cool. And just to clarify again, right? The reason both algorithms work is because, so the very first edge, it takes 1. Okay, there is no cut we're considering. We're just taking the cheapest edge. Okay, so just assume that works. And then that one is going to connect. Essentially, there's a cut that cuts these two vertices away from the other ones in the graph. And then it considers out of the remaining edges, it turns out this 2 is the cheapest one to take next. Yeah. Prims will, by construction, it also avoids cycles because it only considers edges that are going from a node I've already included to a node I have not yet. So for example, when we did A, we took A and B, we were only looking at the only candidate edges were from A to C, B to C, and B to D. We were not, A to B was not a candidate because it already connected nodes that were in our tree. So we only ever consider edges going to nodes we don't connect. But yes, but you do have to like avoid, you don't want to create cycles. You can never create a cycle. Yeah. Because if you have a cycle, it's not a tree. Which I think that's it. Oh, and what is the weight of the minimal spanning tree? 16? Okay, I believe you guys. All right. So hopefully you guys are pretty comfortable with minimal spanning trees. Let's get started with lecture today. We're going to cover more stuff about maximum flow and cuts. So homework 9 is not due today. It is due tomorrow, 4/21. There is a walkthrough available as well. And if you have questions for me, I'll be in my office the rest of the day today, or I'll be in Eric. So just come ask me anytime. Yeah. End of the year survey, if you guys could fill it out, that would be great. And final reminder, our final exam is on Wednesday, 5/11 from 12 to 2. It's going to be in person in class. So make sure you start studying now. Okay. All right. So today we're going to cover max flows and minimum cuts. Just as a reminder from last time, I did do a little bit more digging. I guess let me minimize this so you can see. Yeah, there we go. We were talking about how this algorithm was actually developed in 1955 in order to identify what are the minimum number of railways that we need to blow up in order to disconnect the eastern part of Europe from the Soviet Union, right? So I did a little bit more digging, and there is a book somebody wrote, and this is the part that's kind of interesting. So there was a paper that they published that discussed the algorithm. So the paper was published publicly in 1955. They have this quote in that paper. A particular problem as the central one suggested by model, and then they have a reference 11, okay? Reference 11 is actually a reference to this report, which was marked secret, and it was not released until 1999. Called the Fundamentals of Method for Evaluating Rail Net Capacities. So again, in case you guys didn't believe me last time, this is how it happened. This is now public. You can look it up online. You can read the original paper if you're interested in that, but it was marked secret at some point. And so we had this graph last time. I think we got to the point where we figured out the maximum flow. It turns out the maximum flow for this graph is 11. And this is the flow. So again, just to clarify, for each graph, what we have is we have a number that corresponds to the capacity of that edge. And then we also have a number in the box that corresponds to how much is flowing through that edge. So this is the maximum flow for this graph. Okay. You cannot push more flow from S to T. It is 11. It turns out that 11 is also the minimum cut of this graph. Can somebody see what is the minimum cut, the minimum ST cut of the graph? So again, an ST cut is a cut that separates S from T. It has value 11, which means the edges going across the cut is 11, and that is the minimum. And again, an edge contributes to the cut only if it's going from S to T. So if you have edges that are going from T to S, like backwards, they don't contribute to the cut cost. So Yeah, Leander? So yeah, top left, so here, and then 3 in the middle, and then 4 at the end. Yes. What is, and the cost of that cut that you just described is what? It's 11, because it's 4 plus 4, 8 plus 3, 11, right? So this edge, and this edge cross the cut. These edges are going backwards. They're going from T to S, right? So they're going from the side that T is on to the side that S is on. So they don't count towards the cost. Now, the main reason I point this out is it turns out this is the minimum cut. And its cost is 11. The maximum flow on this graph is also 11. Okay. Why do you guys think the minimum cut is equal to the maximum flow? That's all right. We're going to talk about it. So let's keep going. You guys should have known it's a coincidence, but it's actually not. But yeah, what's that, Jonathan? Yes. So the maximum flow for this graph, which is what is the maximum amount of material I can push across my edges, right? So each edge, so from S to T, I'm trying to push some amount of resources. The maximum I can push for this graph is 11, and it's actually given by these flows. Okay, so I've already given it to you. Now, alternatively, I can also ask the question, what is the cost of the minimum ST cut? So a cut of the graph that separates S from T. The minimum one has cost 11 as well. So the question is that just a coincidence, or is there a reason why the minimum ST cut is equal to the maximum flow?
Is that sort of like you're always taking the path of least resistance?
A little bit, yeah. Keep going along that logic. So you can't say path of least resistance, but your flow has to cross.
If you have the shortest path, can't you put more resources because you're going to like quicker, so you can always like push more resources.
All right, continuing on. So one way to think about it, and we're going to cover this in more detail, but keep this in the back of your head. Your flow is going from S, that's where everything is originating, and it has to get to T. So everything has to make it into T. That means it has to cross all the cuts on the graph, right? If I cut the graph like this and I split it, this has to have enough capacity so that the flow can make it through. So the maximum flow has to be at most, it can be at most the cost of the minimum cut, right? So that doesn't tell you why it's equal. You also have to argue the other way, but it is at most the minimum cut. So yes, you guys are right. So this is the cut, as Leander mentioned. So good job calling it out. There is something called the max flow min cut theorem that tells you that the value of the maximum flow is equal to the cost of the minimum ST cut. Okay. So the intuition is that a max flow, that the minimum cut better fill up because this is the bottleneck. Okay. Now we're going to try to prove it. So the first thing we're going to prove is we're going to prove that the maximum flow cannot be more than the minimum cut. And that's what we were just talking about. Intuitively, that should make sense. I cannot push more stuff than can go across some cut, right? If I consider all the cuts I can make, right, the maximum amount of stuff I can push has to go across all of them. So it cannot be more than the smallest cut. Okay. What we actually want, what the theorem actually says, is that the maximum flow is equal to the minimum cut. But we're just going to prove this part right now. The other part is you have to prove that the minimum cut is at most the maximum flow. Okay. Which we're actually going to do by showing an algorithm that constructs a maximum flow or constructs a cut based on flows. Okay, so for any ST flow and any ST cut, right, the value of the flow is at most the cost of the cut. Hence, the maximum flow is less than or equal to the minimum cut. And this is called a proof by picture, which is you've got stuff coming out of S. It's going to go to some nodes. All of that stuff has to go into T, right? So for any cut, the cut has to be big enough so that all the stuff can make it across, right? So this is just a random ST cut. It's not the minimum, just a random ST cut. This, the cost of the cut, so the value going from S to T, right, has to be big enough so that all of the flow can make it across. Otherwise, the flow would have to be less, right? Because then you can't make it all to T. Does that make sense? This is a proof by picture. Hopefully yeah. Okay, cool. So X has to be less than or equal to this cut. Okay. It is a good exercise for you guys to try to convert this to an actual proof. So like write it out mathematically or like logically think about it. Okay. This is the second part. So the theorem is stronger. The theorem actually says that the maximum flow is equal to the minimum cut. It does not say that it's at most. We'll prove this by algorithm. So here's the question for you guys. I give you a graph and I want you to find the maximum flow. How would you do it? You're just trying to find out. So this is the graph. For this graph, we actually already worked it out. The maximum flow is 11. I give you guys the answer. But you are just given the graph. How would you try to figure out what is the maximum flow? Yeah, David? Closest edges to S? Not really. So all of the, so 6, 2, 4. So if you add these up, that's actually 12. Maximum flow is 11. Yeah. Yeah, so you both are on the right track. So one idea is like, let's look at we want to take into consideration the capacities of our edges. I think that's what David mentioned. One first step is let's just try to push as much as we can from S to T along some path, right? So what you might do is, well, let me find a path. Let's say, this one that goes from S to T, right? Then I can push 3 units of flow along that path, right? So your flow is at least 3, okay? And then what would you guys try to do next, maybe? So first, find some path, push as much flow as you can. So that means that along this edge, I'm pushing 3. I'm pushing 3 along this edge, and I'm pushing 3 along the last edge, right? What might be my next step in the algorithm? Or like, yeah. You might try to repeat this, right? You might try to find more paths to try to push more flow. So maybe you modify your graph so that instead of 4 here, you have 1. Because now there's only 1 capacity left over, right? Instead of 3 here, you have 0. This edge disappears because you cannot push any more through that flow, through that edge, right? And then you modify this edge to be 1 because you can only push 1. Yep. Question? I just took an arbitrary path. It could be, yeah. I'm not trying to be smart about it. There are 2 ways. You're getting a little bit ahead of yourself. There are 2 really good ways to pick paths. One is the shortest distance, DFS. The other one is pick the fattest path. So pick the path that can carry the most capacity. Okay. It turns out you can pick paths however you want. This algorithm will work. Yeah. Huh? 3. I pushed the most I could along that one route, which is 3 because that is the minimum capacity along the edges. Yeah, that is why I pushed 3. So you guys you're very close. You're almost discovering the full algorithm. Okay, so you might then do this again, right? Find another path and try to push some stuff. So maybe you say, let's take, let's go up this way, then down, then across, right? The problem with that is I can only push 1 more capacity, right? Because this edge only has capacity 1, because I'm already pushing 3, so now I'm going to try to push 1 more. So now this edge goes to 0. This edge has flow 1. This edge has flow 4 now. The capacity goes down to 5 because I'm already pushing 1 through it. And then for this edge, the capacity goes down to 3 and I'm pushing 1 through it. Okay. So now my flow is 4. Okay. So we're getting better. We're getting better and better. Okay. So keep that in mind. This is the first half, or this is most of the algorithm is basically this. Find a path, try to push as much through it as you can, modify your graph so that it takes into account the fact that some of your edges can carry less stuff. The one difference, I'll actually talk about it in the slides. So let's see what the next slides are. The one thing, this is called the Ford-Fulkerson algorithm. This is the algorithm that was in that paper that we discussed. This is what it does. It starts with a flow of 0. Okay. What we're going to do is we're going to maintain a graph. So this is the modified graph. This is the graph we're going to modify called GF. This is just a mathematical symbol called the residual graph. The first thing we're going to do is we're going to find a path from S to T that will give us a way to improve our flow. Now, you guys have, like, what algorithm would you use here to find a path from S to T? Given a graph, how would you find a path? Yeah, what was that? Yeah, DFS, BFS, right? Like I mentioned, when you guys learned those algorithms, we use them in more complicated algorithms. So here you would say, you know, run BFS on this graph to give me, starting at S, to give me a path to T, right? We're going to keep doing this until there's no more ST paths, until we can no longer find a path, which means we cannot push any more flow. Okay, skip that part. So here's an example. This is what a residual network is. Okay, this is a normal graph. This is not the residual network yet, but this is a graph with a particular flow. So I'm already pushing stuff through it. I'm pushing 1 unit through this edge, 3 units through this one, 1 unit down, 2 units here, 2 units there. Okay, so this is like somewhere in our algorithm, we're already pushing stuff. Now, I mentioned in the previous slide, I mentioned this residual graph. Okay, so the residual graph is this. Who can tell me how I went from this graph to this graph? And you guys already did half of it before when you were discovering the algorithm. There was just one part that you guys missed. Yeah. Yes. So for all of the edges that still have capacity left over, I changed their capacity to be equal to the original capacity minus how much I'm pushing through it. So instead of it being 4, this now has capacity 1. Instead of being 8, this now has capacity 7. Why? Because I'm already pushing one flow through it. Okay, so now it doesn't have 8. It can only fit 7 more. And what we also do is we add additional edges going in the reverse direction that have capacity equal to our flow. So this edge has capacity equal to 3. This edge has capacity equal to 2. Why do you guys think we do that? Trying to keep track of stuff. That's one choice. Why else? That's a good suggestion. You might want to analyze like the backwards flow. It's actually a lot simpler than that. The reason we add these extra edges is because you might have not picked a good path when you started. You might have tried. So for example, I forget what the optimal solution is, but I don't think it pushes 4 units through this edge. I think it only pushes 3 or something, right? But if you first find this path and you try to push 4, you're kind of stuck. So basically there are edges where you might find a path and you try to push as much as possible, but it is actually not optimal to push that much weight through that path. So you want to give the opportunity for the algorithm to undo its decisions. So these edges, they're treated the same way. They're normal edges. They're just going backwards and they have a capacity. So what can happen is the algorithm can choose, instead of pushing 3, If it pushes stuff back over this edge, it is basically saying, I want to push less flow through that edge. Okay. So this forward edge is capacity minus flow. Backward edge has just the normal flow. And backwards edges are the amount that's been used. Forward edges are the amount that's left. Okay. So that's called a residual graph. They tell us how to improve flow. In this graph, a path from S to T is called an augmenting path. So this is the path where I can still push more flow. Okay. The claim is if there's an augmenting path, we can increase the flow along that path. So for example, here in this graph, there is a path from S to T going from S to here. So you follow this edge, then you take this edge down, then you take this edge over. So I can actually still push more flow, like one more flow along that path, right? Yep. Okay. Let's skip a little bit of this. I think an example would be the most useful for you guys. Well, okay. Yeah. Okay, fine. We'll go through it. Okay. So what the algorithm does is it tries to find a path from S to T in my residual graph. So here's a path I picked. Okay. Now, what the claim is that that path in the original graph means I can push extra flow through that path. And you guys should be able to see that you can push an extra unit of flow along this path. So in this case, all of the edges along my path are the normal forward edges. So it should be pretty obvious to you that if the path exists, then I can push extra flow equal to the minimum weight of the edge of an edge along that path. Okay. Because forward edges tell you how much stuff can still go through. Now, the other case, right? So this is what we do. So our original flow is 3, 1, 2. We just increase them all by 1, and that's still a valid flow. Okay. The harder case is when the path that you pick has backwards edges in it. Okay. So here's a different example for a different graph. Suppose this is the path that you pick now. So this path, you'll notice, it goes along this forward edge, but then it goes along this backwards edge, this black one, and then along a forward edge. Okay, and this is why you need the backwards edges, because what this is saying is it's saying that you can actually push more flow along this edge. So you can increase this edge, the amount of flow you're pushing by 1. For this edge, you actually have to decrease the amount of flow you're pushing. Okay, because that will let you increase the flow overall. So this is the corresponding path. And what you do is we should not increase the flow at all the edges along the path, right? For the backwards edges, we actually need to decrease the flow. So if we tried to increase the flow along all the edges, you would increase this by 1. So now you have 2 going this way, right? If you increase this by 1 as well, you would have 2 going up, right? And you would have, if you increase this by 1, you'd have 1 going out. So that's 2 going up, 1 going out, but only 1 coming in, which doesn't make sense. You only have 1 thing coming in, but you have 3 going out, right? So that's why when you see a backwards edge along the path you picked, you don't just increase the capacity of that flow. What it tells you instead is we add flow to the forward edges and we remove flow from the backwards edges, because that helps us maintain our capacity constraints and our all the amount going in is equal to the amount going out. Okay, so that's what this looks like. So this flow is actually 2, this flow becomes 0, and this flow becomes 1. So with this path, so this path is a little weird. What actually happened is we are now pushing 2 units of flow along the top and 1 unit of flow along the bottom, right? Even though the path that we found was going this way, right? Because we had a backwards edge, which means we actually decreased the flow. Okay. So once you update your original flow amounts, then you can update your residual graph to match your new flows, right? So what does that mean? That means our graph now looks like this, right? Cool. Okay, so this was our original graph we started with. We had some flow. From this graph, we can construct a residual graph as defined. If we find a path in this graph, that means we can push more flow in the original graph. After pushing more flow, this is what our graph looks like. This graph has this corresponding residual graph. Can you guys find a path from S to T in this graph? Yeah, Leander. Yeah, you can push more flow this way. There is a path. Okay. So just because we have so we're not done, basically. We repeat the process. We keep going. Because what happened is you'll notice that every time you do this two-step process, so start with a graph, create the residual, find a path, push more flow. The flow will always increase. So for the original graph, we had a total flow value of 2. For this graph, we now have a total flow value of 3. Okay. And the other thing, the reason we need to keep the backward edges, this is still a valid flow. Like it does not violate any of the constraints about you have 1 going in, 1 going out, 2 going in, 2 going out, right? So nothing broke. Okay. So here's what you would do. If there's an augmenting path, we can increase the flow. So given a path in the augmenting graph, you find the minimum weight along that path. So what is the maximum I can push through along this path? If your edge is a forward edge, you just add the flow. You add that x, that minimum, to your edge. So you push. So if your edge in the augmenting graph is going forward, then you push that much more amount through the edge. If it is going backwards, then you subtract that amount from the edge. Okay, that is how we augment a graph. I'm low battery. Should have enough. We only have 2 more minutes. Okay, so here's an example. This is some path that you found from S to T. The minimum weight along that path is 2. So what that means is that for every forward edge, we can increase the flow by 2, right? So this gets increased to 4, this gets increased to 3, this is a backwards edge, so we decrease the flow by 2. This gets decreased to 1, this gets increased to 2, okay? And this new flow is still valid, where we have 4 units. I guess originally we had 2 units going in, 1 unit going out. So that means there should have been another edge somewhere that had another unit going somewhere else. Okay. And we still have that, where we have 4 units going in, 3 units going out, and then 1 unit going somewhere else. Okay. This is our new flow called F prime. And that is the Ford-Fulkerson algorithm, is to do all of that. And that is how you find the maximum flow in a graph. So you start with a flow that's all 0. You create the augmented graph, the residual graph that we called it. While you can find a path from S to T in your augmented graph, find that path, increase the flow along that path, and then update your augmented graph, and then repeat until you can no longer find a path, and that is the maximum flow. Okay, so a couple of things. This is probably one of the most complicated algorithms that we have covered in the class so far. But the complexity, hopefully, when I say find a path from T to S, you are able to think in your head, okay, that's just BFS. That's just DFS. So we're building up on stuff that we have already covered. I think it would be a great homework assignment to code this up. What do you guys think? Yeah, yes, okay, good. All right, so that's all of the time we have for today. This is called the Ford-Fulkerson algorithm. We just covered the basics. It is really useful in a lot of stuff. We're going to cover, we'll do it on Friday, I guess, but we're going to cover applications of where finding the maximum flow, which to you, it's like, well, obviously for railroads, that's kind of useful. It is actually useful in a lot of other domains. You just have to think of the problem as a flow problem. Cool. All right, thanks for coming, guys. That's it for class today. I'll stop sharing. All right, see you guys on Zoom. Bye.